Hello, I am Abdurrahman Al-Huwaikim.
I'm Brady Fry,
I'm Hassan Al-Wahimid.
and we're Group 13. Our project was to develop a real-time seating availability system for the Valley Library. In this presentation, we are going to talk about three things. The first one will be from Abdul, where he will talk about a project overview and tell you about the problem that we had solved, that we had designed for, and our solution for that problem. He'll also give you a general overview of how the system works. Next, we'll hear from Hassan, and Hassan will talk about the engineering requirements, and those are the benchmarks that we designed for. After that, we'll have a demonstration of our product where you'll be able to see it in the field actually working.
One of the essential components of being a successful student is reserving ample time to study the materials you have learned. The Valley Library is a great facility to accommodate studying space. During peak studying times of the year, there is a lot of competition between students to find studying space. Often, students spend precious time searching all 6 floors looking for that space. So the problem we are trying to solve is to graphically display table availabilities in the library.
So there's a few design choices we made during the process that we like to point out. One of the first ones was power. Power is important for any electronic system. We were looking at either having a wall wart, powered directly from the wall, or batteries. Now batteries are intriguing because it gave us mobility, which is key to how the chairs and tables move in the library, because the students do move them around for their specific needs. But a downside of batteries is they discharge, which means they would need to be replaced, which would be a high maintenance cost, and we didn't want a high maintenance cost, so we went with constant power and having a wall wart directly power the sensor system 24 hours a day, 7 days a week. Another design choice we made was placement of the sensor. We had a few designs we were looking at when we were just trying to decide what we wanted to measure. We could have measured chairs for the highest accuracy, or we could have put the sensor in the ceiling for least obtrusiveness for the library itself. But we went with a balance. We chose for a sensor underneath the table that would allow us to have relatively good accuracy while also being able to move with the fluidity of the tables in the library.
To solve this problem, our team developed a sensor system that monitors the occupancy of the tables and send their status to a server. This server then will graphically display the real-time availability of the tables and their location in the library. Our system consists of 4 major blocks. The first block being the sensor block. Our sensor is a passive infrared sensor, or PIR. It detects the heat radiation emitted by the body, so if there's a change of the background temperature, it outputs a digital high, otherwise a digital low. Of the operation. If it receives a digital high from the sensor, it processes the data and decides whether the table is occupied or not. Then it sends two pieces of information to the Wi-Fi module. The information being the serial number, a unique serial number, and a status. The microcontroller sends the data to the Wi-Fi module. The Wi-Fi module is connected to a server where there is a database that receives this data and stores them. Then we have a web page that takes this data and represents them graphically to students. In conclusion, this is how our system works. We designed our system to fit the application, keeping in mind simplicity and cost efficiency.
Every project has its unique requirement. For our design, we have 10 engineering requirements that are critical for its completion to satisfy the customer. Our first engineering requirement is having a monitoring occupancy of each table at 80% accuracy or better. Let's assume that we have 5 attempts to occupy a table. 4 of them should be accurate and correct out of the 5. So we make sure that the table is occupied. The second engineering requirement is having a server update within 30 seconds of status change. So the time of the attempt to sit at a table and settling down will take about that range. So that system will update on that time. The other engineering requirement is having a web page that show the availability of each table and their location graphically, so to ease the search of each table or of any table through the 6 floors without having any problems. One of the critical things is when someone is passing by a table and it detects that, so we account for that error. Our fourth engineering requirement is the system will not detect any movement within 20 inches away from any edges of the table. So if anyone pass by walking, the system will not detect that movement. The fifth requirement is accounted for the cost. The cost of the system will be less than $120, so the system will be affordable for a larger scale when it's implemented for libraries. The sixth one is mounting and unmounting the system should take less than 3 minutes to make the maintainability less and for a faster maintaining the devices. So going from a table to another table will take time. In larger scales, this will take more time and more building up if we have more than 3 minutes. But to design for less time for the maintainability, we will have less than 3 minutes. On the power side, our system should operate between 9 volts to 14 volts. And designing the device to be at that range will give the customer the flexibility to change the wall wart when it breaks. So the customer will not worry about what type or what value of voltage the wall wart should give out. Our next engineering requirement is having a PCB that's size within 5 inches by 3 inches, which makes us really small and to fit in a small box. For the system robustness, the ninth engineering requirement that states that the enclosure should withstand a 40 inches fall, so that if any accidental fall from the installation or if anyone carrying it and it falls down, the system should stay safe. And the last one is having an enclosure size within 10 by 6 by 3 inches. So it will be small enough to mount it under the table without taking any more spaces or making any obstacles for the students when they sit at any table. In conclusion, we come up with this system that meets all these specifications to make a more robust and accurate monitoring system that will serve the library for the future.
In this segment, we are going to demonstrate our sensor in a real environment. So the sensor gets placed under the table, away from the view of the students and away from their direct interaction with the sensor system. So we are going to show you one of 3 things. First, it's going to be when a table first gets occupied. So a student will come down, sit, and we'll show you how. We'll just show you the table, the student, as well as the web page updating showing this table is occupied. Next, we'll show you when the student leaves and when the table becomes unoccupied, and see that the web page updates like so. And then thirdly, we don't want somebody walking by to trigger the sensor, so we'll show you that somebody walking by will not trigger the sensor and the table will remain unoccupied. An important part of our product demonstration is the actual product itself. As you can see, the box is designed to be very minimal in size. This allows it to be modular and easily replicated. We also had a few other constraints that we designed for in the size. Is we wanted it to be unobtrusive. So product placement underneath the table, looking across the table, is very important for accuracy, as well as a box you didn't want sticking 1 foot out. This gives us the highest accuracy and the lowest unobtrusiveness in our system. We told you about our project. First, we had Abdul give you a general overview of our project, the problem that we faced, and our solution to that problem. And also he gave you an idea of how it works, how it was put together. After that, we had Hassan, who told you about our critical engineering requirements that we needed to design for and pass so that we could graduate. And then we had a real-time demonstration of our project that showed you it in the field actually working. We hope you enjoyed this. We're definitely glad that it's over and that we have a project that we can be proud of. But before we go, a little parting advice for the graduating seniors of next year.
Communication. It's the key to success. Keeping your teammates well informed and up to date about your progress is critical. Lack of communication may cause your whole project to delay or ultimately to fail.
My advice to you is try to make a happy team. So when everyone does something correct or incorrect, just to try to motivate them. Making a happy team will make a successful project. Making a successful project eventually will graduate.
My advice to you is about your attitude. So you're coming into this project and you're moving away from a very structured classroom environment where things are you're told what to do, how to do it. You get to be managers of your own project. And with that is going to come a lot of learning experiences. You're going to be able to, if you're active, find out very quickly what deficiencies you have and what deficiencies your group project members have. Try to have a positive attitude. Understand that all three of you are learning and trying to graduate, and be an example of positive affirmation as well as trying to build on the weaknesses and make them strengths.